Hi, I'm Patrick Reagan, and welcome to the Network Switches Part 2 Switches. In this video, we'll explore the essential features of network switches and how they operate in modern networks. From the basics to more advanced topics, I'll guide you through the key switch types, including unmanaged and managed switches, Layer 3 switches, multi-layer switches, and even power over Ethernet. As always, stick around for the practice questions at the end to test your knowledge and reinforce what you've learned. If you find that this video is helpful, don't forget to click the like button. And if you have not already subscribed, hit that subscribe button and join the Pat Has Your Back community for more tech training content. A network switch is a device that connects multiple devices within a local area network or LAN. It functions as a multi-port bridge with each port representing its own collision domain. This means each connected device enjoys a dedicated communication channel, so there's no need to compete with other devices for bandwidth. Switches are widely used across environments, from homes to small businesses to large enterprise networks, to link together computers, printers, servers, and other networked equipment, enabling efficient and organized data exchange within the LAN. Network switches also offer scalability by allowing multiple switches to be interconnected. This creates a larger, more capable network that can support additional devices and traffic without sacrificing performance. In addition to expanding capacity, switches help enforce network security. They support features like port security, which restricts access to specific devices, and VLANs, or virtual LANs, which segment traffic to isolate departments or sensitive data, keeping your network both efficient and secure. Switches significantly enhance network performance by reducing collisions and enabling full duplex communications. Unlike hubs, which only allow one-way communications at a time, full duplex mode lets devices send and receive data simultaneously, doubling the efficiency of each connection. Remember, Ethernet cables have separate channels for sending and receiving data. Switches take advantage of this by dedicating each port as its own collision domain. That means traffic is isolated per connection, minimizing interference and ensuring data moves quickly and smoothly across the network. Switches operate at Layer 2, the data link layer of the OSI model. They use MAC addresses to perform packet switching, ensuring that data frames are delivered only to the intended destination. Rather than broadcasting data to all ports like a hub, a switch filters and forwards frames based on the destination MAC address. Note, broadcast packets will be sent to all other ports except at the port it comes from, which means the switch consists of a single broadcast domain. It does this by using MAC address table, also known as the Content Addressable Memory, or CAM, or a forwarding database, or FDB. This table maps each MAC address to a corresponding switch port, allowing precise and efficient data delivery. When a packet arrives at a switch, it reads the source MAC address and records it in the MAC address table, mapping the device's MAC to that port which it came from. The dynamic learning allows the switch to maintain an up-to-date record of which devices are connected to which ports. Then, using the destination MAC address, the switch forwards the frame directly to the corresponding port, operating entirely at Layer 2 of the OSI model. For example, if Computer 1 wants to communicate with Computer 4, the switch receives the packet and forwards it directly to Computer 4's port. Meanwhile, devices like Computer 2 and Computer 3 remain unaffected. The network links stay idle and uninterrupted, ensuring a smooth and efficient flow of data. A network switch gets its name from the process of packet switching, where data is rapidly sent from one port to another. This switching happens so fast that it appears every connected device is communicating simultaneously, ensuring smooth, efficient data flow across the network. Modern switches support incredibly fast port speeds, typically starting at 1 gigabits per second and scaling up to 10 gigabits, 40 gigabits, or even 100 gigabits per second per port, delivering the bandwidth needed for today's high-performance networks. Modern network switches are capable of handling massive volumes of packets simultaneously thanks to their high-speed internal architecture. The exact number of packets a switch can manage depends on several factors, including its switching capacity, also known as the backplane bandwidth, port speeds, and processing power. High-end enterprise switches can process thousands or even millions of packets per second, ensuring consistent performance even under heavy load. This capacity is what allows large networks to stay responsive even with dozens or hundreds of devices communicating at once. Key metrics for evaluating switch performance under heavy conditions include switching bandwidth and packet forwarding rate. Exceeding the switch's capacity can lead to packet loss or performance degradation. Switching bandwidth refers to the total volume of data a switch can handle across all its ports per second, typically measured in gigabits per second. It represents the maximum data throughput the switch can deliver under ideal conditions. Because switches support full duplex communications, sending and receiving data simultaneously, the calculation usually involves doubling the total bandwidth of all ports. For instance, a 24-port switch and 1 gigabit ports has a switching bandwidth of 48 gigabits per second because 24 times 1 gigabits per second times 2 equals 48 gigabits per second. However, this potential is constrained by the switch's backplane capacity, which is the internal highway that moves data between ports. If the backplane isn't fast enough, it becomes a bottleneck, limiting actual performance despite high port speeds. Packet forwarding rate measures how many packets a switch can inspect and forward per second, typically expressed in packets per second. It reflects how efficiently the switch processes each data packet, especially under heavy network traffic. The rate can vary based on packet size. Smaller packets generally require more processing per second, so a higher forward rate is necessary to maintain throughput. That's why understanding this metric is key when evaluating a switch's real-world performance, not just its theoretical bandwidth. Switches rely on buffer memory to temporarily store packets during transmission. This buffering is especially valuable to networks with bursty traffic where sudden data spikes could otherwise overwhelm the switch. Larger buffer sizes help absorb congestion, preventing packet loss and ensuring smoother communications. Another key performance factor is processing delay, which is the time it takes for a switch to analyze a packet and forward it to the correct port. Switches with low latency provide faster response time, which is essential for real-time applications like VoIP, video conferencing, and online gaming, where even slight delays can disrupt the user experience. When configuring switch ports, you want to pay attention to a few key settings. Speed, which are options typically include 10 megabits per second, 100 megabits per second, 1 gigabits per second, or 10 gigabits per second, depending on the switch and connected device capabilities. Duplex mode, where you choose between half duplex, where data flows one way at a time, or full duplex, which has simultaneously send and receive. Most modern switches and network devices support auto negotiation, allowing them to automatically agree on the best speed and duplex settings. However, in some environments, especially for performance tuning or troubleshooting, manual configuration might be necessary. Just remember, both ends of the link must match. If one side is manually set and the other set to auto, it can lead to a mismatch and cause performance issues, even link failures. Switches come equipped with multiple ports, commonly 4, 8, 24, and 48, or even more, to support a wide range of connected devices and networks, both small and large. These ports can be Ethernet RJ45 ports using copper cables for typically LAN connections, or fiber optic ports, which support longer distances and higher data rates, which are ideal for backbone or uplink connections. Most modern switches support auto negotiation, meaning they automatically detect and configure the highest compatible speed in duplex mode with the connected device. For example, a switch might auto-configure to 1 gigabits full duplex if both ends support it, optimizing performance with minimum manual setup. There are two main categories of switches. Fixed configuration switches provide a fixed number of ports and are typically not expandable, which makes them less expensive overall. Fixed configuration switches include unmanaged switches, smart switches, and managed switches. A smart switch is a subtype of a managed switch that has basic management and configuration options. Modular switches offer maximum flexibility and scalability by allowing you to add expansion modules as your network evolves. These modules can be tailored to specific needs, such as integrated firewalls, wireless controllers, or network monitoring tools. Beyond functionality, modular switches can also support additional interfaces, redundant power supplies, and extra cooling systems, making them ideal for high availability environments. While this level of adaptability comes at a higher cost, it provides the robustness and customization required in large-scale or mission-critical networks where future-proofing is essential. This type of switch provides you with the most flexibility, but at a higher cost. Standalone switches are individual devices that operate independently within the network. They're commonly used in small-scale environments or positioned at the edge of a larger network, for example, to connect a small group of devices in a branch office or work group. Because they function autonomously, standalone switches lack advanced stacking or clustered capabilities. That means they can't be managed as a single unit with other switches, which limits centralized control and scalability, but also keeps deployment simple and cost-effective for the right use case. While a stackable switch can operate as a standalone switch or can be stacked where multiple stackable switches are managed as a single entity. Stacking is a scalability mechanism where the switches are combined via a dedicated stacking port and stack cable to operate as one logical unit and share the same IP address. By setting up a group of stackable switches, you can add extra available ports on your switches, simplify network configuration and structure, eliminate loops, and improve reliability. If any part of the stack fails, the stack will route around the failures so your network keeps running. This model is suitable for small to medium-sized businesses or branch offices where future network expansion is limited. Stackable switches can be interconnected using various high-speed links, such as direct attach cables, active optical cables, or fiber optic connections with transceivers. These physical connections form the foundation for stacking topologies, with the most common being chain topology, where switches are connected linearly, which is simple to implement but vulnerable if a link fails mid-chain, and ring topology, which provides higher reliability by forming a closed loop. If one link fails, traffic can reroute in the opposite direction, keeping the stack operational. Within a switch stack, there are two roles. The stack master is the primary switch that manages the entire stack. It holds the running configuration, performs system-wide updates, and provides the management interface. Stack members or slaves are the other switches in the stack that act under the direction of the master and don't require separate configuration. Users manage the entire stack through the master switch interface, simplifying configuration and monitoring. In the event the master fails, the stack elects a new master from the remaining members, maintaining uptime and central management with minimum disruption. An uplink port is a specialized Ethernet port on a network switch designed to connect to higher-level devices such as routers, core switches, or servers, extending the reach of the local network. Uplink ports can also connect lower-level network devices like other switches or hubs, helping expand the network laterally. These connections are often designed for interoperability, allowing switches from different series or vendors to link seamlessly. That said, modern switches often don't require dedicated uplink ports. Instead, any regular port, especially those with RJ45 or SFP or fiber interfaces, can serve as an uplink, offering scalability and flexible network expansion options. Don't confuse switch stacking with switch trunking. They serve very different purposes in a network. A trunk is a communication link, usually Ethernet or fiber, that carries multiple signals or VLANs simultaneously. Trunks are used to connect switches or network segments, providing network access between 2 points. Think of it like a trunk of a tree carrying data to and from many branches. Switch trunking allows a set of shared links to connect multiple switches instead of a dedicated separate links for each. Trunk links are commonly used to carry VLAN traffic between switches, routers, or other network devices, offered leveraging IEEE 802.1q tagging, a layer 2 of the OSI model. Trunking can also refer to link aggregation, where multiple physical links are combined for higher bandwidth and redundancy, enhancing both performance and resilience. Connecting the switches, you would choose a port on each switch that will be part of the trunk connection. You then configure these ports as trunk ports. On each switch, specify which VLANs are allowed on the trunk port. Ensure that the VLAN allows on the trunk port are also configured on the switches. A chassis switch, also known as a modular switch, is similar to blade servers, where it is configurable with various types of line cards to provide the type and quantity of required network ports. Chassis switches offer superior scalability options due to the large size and modular nature, which has a certain number of fixed slots which are used to insert different types of line cards. They allow you to add more line cards or modules to increase port capacity and network capabilities as needed. This feature makes them particularly suitable for data centers and large enterprise networks that anticipate significant growth. Chassis switches are engineered for maximum reliability and performance, making them the go-to solutions for core network infrastructures in large data centers and enterprise networks. They typically feature redundant power supplies for uninterrupted operations during a failure, hot swappable fan trays and modules to simplify maintenance without taking the switch offline, and failover capabilities that ensure traffic continuity if one component fails. Thanks to the modular design and robust architecture, chassis switches serve as a central backbone in efficiently managing the flow of massive volumes of data with precision and minimum latency. Switches can be divided into unmanaged and managed switches. Unmanaged, minimum or no configuration options. There's no support for management protocols like SNMP or a command line interface. It's ideal for plug-and-play setups. It's affordable and commonly used in home networks or small offices. These switches are perfect when simplicity is the goal. They get the devices talking without any setup fuss. They do not require IP addresses because they're not used to connect to remotely to manage them. Managed switches are used predominantly in enterprise networks, where managed switches provide extensive control over configuration, monitoring, and optimization. Key features include Simple Network Management Protocol, or SNMP, which enables centralized performance monitoring and remote configuration. Network admins can track port usage, bandwidth trends, and receive alerts when thresholds are exceeded, helping with troubleshooting and performance tuning. Quality of Service, or QoS, which prioritizes critical traffic like voice and video to ensure smooth performance even during congestion. Redundancy via Spanning Tree Protocol, or STP, that prevents network loops and ensures continuous operations by dynamically rerouting traffic if a link fails. And port mirroring sends a copy of network traffic to a designated port for packet analysis or intrusion detection. And lastly, Virtual LAN or VLAN support that segregates network traffic for improved security and efficiency. Managed switches can span VLANs across multiple devices using 802.1q trunking. It may be assigned an IP address if you want to manage the switches remotely. Anytime you work with managed switches, you should change the default password. Default credentials are widely known and can be exploited by attackers. Always set a strong, unique password to protect administrative access. In addition, keep firmware up to date. Manufacturers regularly release firmware updates to patch vulnerabilities, improve performance, and add new features. Staying up to date ensures your switch is protected against known threats. There's nothing to configure on a non-managed switch. However, you'll have to configure the managed switch if you want to use all of its capabilities. The management port on a managed switch serves as a dedicated interface for network administrators to access and manage the switch. This out-of-band or OOB management port is separate from the data ports that handle regular network traffic, providing a secure and isolated way to configure, monitor, and troubleshoot the switch. To manage a managed switch, you can connect to a switch using a serial console, where you connect a computer to a switch using a console cable, typically an RJ45 to serial, and using terminal emulation software such as PuTTY to access the switch's command line interface. For a switch to function and for you to connect your device to a switch, the switch does not need an IP address. An IP address only has to be assigned when you want to remotely connect to a management port of the managed switch to manage it. Your switch is a layer 3 switch that needs to perform routing. Much like a router, you need to configure an IP address to the routing ports. After the switch is initially configured, you can also connect remotely using one of the following methods. Assuming SSH is enabled, use Secure Shell or SSH to provide encrypted command line access over the network. Alternatively, you may use Telnet if your switch supports Telnet, but is considered less secure than SSH because of its lack of encryption. Many managed switches offer a web-based configuration user interface, or GUI, for easy configuration. Layer 3 switches combine the packet switching of Layer 2 devices with routing capabilities from Layer 3 of the OSI model. That means they can perform inter-VLAN routing, enabling communications between different subnets. It makes decisions based on IP addresses instead of just MAC addresses. It determines optimum paths for data across multiple networks. While they may include features like quality of service and access control lists, they usually lack the comprehensive security policies, network address translation, or WAN interfaces you find in traditional routers. Why use them? They're purpose-built for high-speed routing between local subnets like departments or VLANs on a LAN, offering faster throughput and lower latency than a router in many enterprise deployments. Routers, on the other hand, are designed for more complex routing tasks and often operate at lower speeds compared to Layer 3 switches. A multi-layer switch does more than just Layer 2 and Layer 3 duties. It can also handle Layer 4 through Layer 7 functions, combining high-speed switching with advanced traffic intelligence. Key capabilities include Layer 2 and Layer 3 switching and routing, which are standard data forwarding and inter-VLAN routing. Quality of service, or QoS, which prioritizes traffic by type of application to maintain consistent performance. Load balancing and security features, which distribute traffic intelligently and may include firewall level protection. And deep packet inspection, or DPI, that allows inspection beyond headers, enabling application-aware policies, bandwidth management, and threat detection. These switches are built for high performance and ultra-low latency, making them ideal for large-scale, mission-critical environments. Common deployments include enterprise network, where it acts as both switch and router to streamline complex, multi-VLAN designs, data centers that handles massive traffic loads with precision, offering granular control over application flows, and campus networks that connects multiple buildings or departments with seamless high-speed routing and switches. A Power over Ethernet, or PoE switch, supplies both data and electrical power over standard twisted pair Ethernet cables, eliminating the need for separate power adapters. This is especially useful for devices installed in hard-to-reach places, including VoIP phones, wireless access points, IP surveillance cameras, networked lighting, and other IoT devices. PoE simplifies installation and reduces clutter, making it ideal for smart environments and streamlined infrastructure. For using a non-PoE switch, you can still power compatible devices with PoE injectors. These sit between the switch and the device, injecting power into the Ethernet cable while letting data flow uninterrupted. Question: how many collision domains do you have for a 12-port unmanaged switch? Answer: 12. Question: how many broadcast domains do you have for a 12-port unmanaged switch? Answer: 1. Question: which of the following is a network device that is responsible for separating collision domains? Answer: switch. Question: what should you use if you're looking for a device that's connected to the network and its associated physical network address? Answer: MAC table. Question: a system administrator wants to use the least amount of equipment to segment two departments that have cable terminating in the same room. Which of the following would allow this to occur? Answer: layer 3 switch. Question: what device would you use to find PoE on? Answer: switches. For more information, visit these sites. In summary, a switch is a device that connects devices in a network to each other, which acts as a multi-port bridge where each link has its own collision domain. Traffic is forwarded based on MAC addresses, which is data link layer or layer 2 of the device connected to the switch. A switch is called a switch because it uses packet switching, which sends packet from one port to another very fast, so it looks like every device connected to the switch is communicating at the same time. Some switches are known as layer 3 switches, which have routing capabilities and can operate at the network layer or layer 3 of the OSI model. A power over Ethernet or PoE switch provides power over twisted pair cabling to our network devices, including VoIP phones, access points, surveillance cameras, lighting, and other IoT devices. Thank you for watching this video. The next video will be switches, part 3, managed switch advanced features. If you like this video, click the like button, and if you have not already, subscribe to the Pat Has Your Back channel. Thank you.